So you want to solve a um, linear transformation sort of change of variable in this question. And so how do we start? Again, when we're changing the variables, it's because either the integrand is bad or the shape of the integration, the region is bad. And in this case, let's draw the shape of the integration. So x and y, and I see y equal to x, y equal to x minus 2, y equal to x is like that, and y equal to x minus 2. And then I see y equal to negative x and y equal to negative x. So y equal to negative x and y equal to negative x plus 3. That's 3. And seems like naturally, if I bring, let's see, if I get these two and do this is y plus x equal to 0, that one is y plus x equal to 3, and then these two come out to be y minus x equal to 0 and y minus x equal to negative 2. Or I can switch this out and write down as x minus y equal to 0 and x minus y equal to negative 2. In either case, you just notice that basically we have this idea of having y plus x to be u, and then y minus x or x minus y to be v. Let's go with y minus x. There's no need to switch at this point. And so that's the idea that I'm getting from the shape of the graph. It's like this region. And then I see if I set that to be u, the bounds for u is going to be 0 and 3. And the bounds for v over here are going to be the negative 2 and 0. So that becomes a nicely done in terms of u and v. We will have, again, we said that negative 2 for v and 3 for u, and they both start at 0. So this becomes the region. Now, what I did is I said g inverse of x and y, that gives us u and v, is y plus x and y minus x. Okay. Now, I either have to solve for u and v, for x and y in terms of u and v, or I have to have my integrand in a good shape. And it turns out, oh, nicely done, this part is actually u, but this part is not. But what I notice about that part is that x squared minus y squared is equal to x minus y times x plus y. X minus y is negative v, and x plus y is u. So this is equal to negative u times v. So that actually works with my linear transformation well. It doesn't require me to do a lot of work. Now, all I need to do is to set up this integral, which is integral over region R of x plus y in terms of u and v. So when I'm setting this up, I set it up whichever I want, du dv, right? This is u. That one is e to the power negative uv. U runs from 0 to 3. V runs from negative 2 to 0. And then I realize I don't have the Jacobian. So how do I compute the Jacobian? Jacobian for linear transformations, there are multiple nice things about linear transformations. Here I didn't have to use this, but I could have just used the endpoints, the corner points, and drew the rectangle over here, and drew the polyhedra over there. Another nice property of linear transformation is that we know that at any point the gradient, I'm sorry, the Jacobian of u and v with respect to x and y is the inverse of the Jacobian of x and y with respect to u and v inverse. That means 1 over. But this doesn't work very well for other transformations, because then it will be confusing. All sort of variables are hanging around. It's not going to work. But it works out well for linear transformations. So all I need to do to find the Jacobian, say here I need to have Jacobian x and y respect to u and v, right? And in my mind, I always remember that the bottom should be related to those two, just like the Calc 1 when we have the basically the chain rule thing. It's always dy over dx times dx gives you dy. So that's what I remember. It's sort of not quite that, but very similar to that, right? It's something to memorize, not the actual math. That's something that I use to memorize. So to find this in here, I find the other way around, which is the determinant and determinant of the u with respect to x, which is 1, u with respect to y, which is 1, and then v was y minus x, right? Y minus x. So v with respect to x is -1, v with respect to y is 1, and negative of that to power -1, find the determinant to power -1, that means reciprocal of that. The determinant itself is 1 minus 1, which is 2 to power -1, which is 1/2. And this is positive, so I don't need to find the absolute value in here. It's just the same thing. But I have to rewrite this as -2 to 0, 0 to 3, u e to the power -uv times 1/2 du dv. Now, the next step in here is to solve. First thing that I do is I realize, oh, the inner integral has, with respect to u, and I have u e to the power with function u inside. And that seems like a lot of work, and actually not a lot of work, it's just the integration by part. But you know, the rectangle is a rectangular region, so why don't I just switch and see what happens? And so I switch the order. And I bring the 1/2 out here. Let's bring the 1/2 out here, all the way out, so I don't have to worry about it for a while. And then I will have u e to the power -uv. Oh, now this is a little bit better. So first do the inner integral. The inner integral will give me u is going to be a constant, so stays constant, then e to the power -uv divided by -u, and it goes from, and I switched that bound somehow. That was 0. So 0, and here is -2 to 0, and this is for v. And so now the next step is, oh, u and u simplify. There's a negative sign out here. put it negative 1/2, 0 to 3. Then I plug in 0 for v, and I get 1. And I plug in negative 2 for v, and I get e to the power negative 2 times negative negative u, it's 2u, and du. So here it's u minus e to the power 2u divided by 2. 1/2 stays, and 0 to 3, which is going to be 1/2. 3 minus e to the power 6/2 minus 0, minus, this is plus, e to the power 0 is 1/2. And that is your final answer. Oops, I just noticed that I forgot this negative sign out here. So there's a negative 1/2 times and negative. And so this is going to be your final answer.